I would encourage all of you to get the PowerPoint thumb drive. The speaker's notes tell you what we wanted to say, not what we did say. So you'll find them to be a little bit more coherent than what you heard from some of us, myself included. Okay, we'll be talking about the SUG, as it's known, and those members of the SUG are the SUGgers. And we have a group of people that are making observations using the one version or another of the FSX spectrograph. And then we're backed up with some scientists, Dr. Reyes, the team, and Dr. Higgins. And our stations are located, as you see, from Florida, South Carolina, Pennsylvania, New Mexico, Hawaii, and Alaska. So we're starting to put together a fairly wide network of spectrographs. And this is the first time that I'm aware of, at least, that there have been spaced spectrograph observations of Jupiter with multiple stations like this. There have certainly been experiments with 2 or 3 stations, but not a wide network like this. So what do? We try to coordinate our observations. We've made efforts to calibrate each of the stations and try and keep control over configuration drawings, data sharing, and generation of storm reports. And Dave has done a lot of work mapping the events that we've received on the IS-CML plane. And we've been engaged in some very interesting science discussions on source physics and signal propagation with Francisco and Chuck and Dr. Teeman. We have a website where we've been posting some of our results and the system diagrams, calibration reports, reference materials, and so forth, as well as prediction bulletins for the prediction for the season, when the storms are going to occur, to help in our planning. As far as the systems diagrams go, it's not that we're trying to make everybody have exactly the same antenna configuration, because everybody has different constraints on what they can put up and what they want to put up and what frequency range they want to cover. So it's kind of a balance between the individual's preference as to what their personal interest is, but yet having a configuration drawings where we know what they have, and so it helps us to merge the data that we get from all the different stations. Here's a relatively simple setup that Tom Ashcraft in New Mexico is using. It's just basically a Jove antenna feeding a multi-coupler, which feeds a couple of receivers and one of the spectrographs. Jim Brown, on the other hand, is trying something a little more complicated. In order to get a wider bandwidth, he's using a Jove, 2 Jove-like antennas, one tuned for 20 megahertz and the other tuned for 24 megahertz, and then combining the signals from both of those. Again, going through a multi-coupler and feeding multiple receivers in the spectrograph. Okay, Dave Typinski, come on down. I hope you all recognize this has nothing to do with Tijuana, and it is, in fact,
I've got a question.
Yeah.
Dick, how do you know about Tijuana? I know that'll be up the louds tonight.
As we were editing this talk, Dick sent me this slide. Yeah, that's about right. Where's our paper? Okay, calibration. As most of you saw out on the lawn the past couple nights, there was a noise source and a step attenuator out there. We used that. Right here is what you saw. We had all the participants run a step calibration. This does assume that you have equal gain across the observing bandwidth, but we figured for enough. Is that your water? So we ran through a step count, and once we got everybody's data back, we were able to generate charts appropriate to each participant's instrument. Oops, wrong button. And for a given color offset to color gain on radio sky spectrograph, we can trace the color shown in the spectrogram back to an antenna temperature. So all these observations are calibrated. And here's some stats for, nice, exciting morning. Let's read spreadsheets. We had actually a whole lot of observations, 151 observations in one season. That's not too shabby. I mean, that's quite a bit. Most interesting is we got several IOD events, or we think might be IOD, we hope. Pretty self-explanatory. This is a typical spectrogram, or histogram you see in most papers that have dealt with the sources on the phase plane. CML3 along the x-axis and just number of occurrences. And it fits really well with the standard definitions of the source regions. Here's one I tried to do in IO phase, just for gee whiz, and now I understand why nobody does this in IO phase, because you really can't tell too much. I mean, IOA and IOC look the same from the left side, so. And, here's your typical phase plane, which we've seen at length. And there is the phase plane of all 151 observations. This just shows each one with the type of emission is color-coded on this. There's just a blown-up region of the IOAC region. There's a blown-up region of the IOB region. And this was all 7 spectrographs, 6 spectrographs, 7, depends how you count them. There's all the L bursting that we saw for the season. There's the N events we saw for the season. S bursting, pure S bursting in this case, which IOB is famous for. And here's some interesting stuff. This was S bursting and N event kind of mixed together. Here is the observations that were right circular. And really interesting, here's the left circular. And what we're curious about is this little area right here. That's that, and possibly even this. We're wondering if that's probably not IOD. Here's some examples of what we have tried as a first cut at coordinating our observations and actually analyzing it. It's fine to take a bunch of coordinated observations, but then what do you do with it afterwards? We're not quite done yet, but here's a first cut. Here's an N event, 12 January, working into December. What we're going to see here, this is the overall storm between 4 stations on the right side of the screen. And we're drilling down in time. I think this is 20 minutes. The first one was like 2 hours. This is a real drilled down view. And you can see there's quite good agreement between all the stations with where the peaks are in time. Ignore the Faraday bands. That's not what we're looking for. We're just looking for gross features like a blob here, blob here, blob here, and kind of a blob there. They agree really well on this storm. On this one, however, a month later, 32 days later, here's the same thing, a real zoomed out view of IOB. This is zoomed in a little more, and already we're starting to see massive differences between these 4 stations. I mean, here I am, and here's Wes. He's only 10 miles away from me. New Mexico, of course, is not near Florida, and Pennsylvania's quite a ways away, too. So maybe you would expect some differences from these two, but you know, what's up with this, over 10 miles, that's quite a difference. And that's, I mean, is this even this, I had to check I literally checked the data 3 times to make sure I was grabbing everybody's correct stuff, because it's remarkably different. And I think maybe the reason is the K-index. That first storm, where everybody agreed the K-index was pretty low. The K-index, for those of you who don't know, is a measure of the disturbance in the geomagnetic field, which affects ionosphere propagation and the ionosphere in general. On the storm where there was a lot of difference, the K-index, it wasn't really elevated that much. It wasn't up into, you know, geomagnetic storm conditions, but it was still elevated. So I think maybe that might have something to do with it, and we're, you know, that's what we're going to continue to look at as we get more and more observations. And that's really it. Any questions about the subgroup? Yeah, go ahead.
Yeah, do you have a method to correlate your stations to assure they're measuring?
I'm glad you brought that up. I had meant to mention that. Andy Mott was going to be here. Unfortunately, he couldn't make it. He was going to present a talk on disciplining a PC's clock to enough accuracy where we could actually correlate the sweeps of these spectrograms at each station. We're not to that point yet. However, that is one of our goals, to be able to do that.
Having spent a career, a lifetime in instrumentation and measurement, two identical instruments taking supposedly identical data in 2 different sites can be greatly different. It has something to do with chaos, because very minute differences in site configuration, weather, all of that can cause these kinds of differences.
Absolutely.
And if you come up with a way to correlate often under those varying conditions, you might be able to correct for some of them.
That's the whole idea. You bet. Okay.
I guess I have a follow-on question to his, and I have another question originally. You indicate that you haven't got the timing issue resolved yet. Is that an issue with respect to recording the data in radio SkyPipe as opposed to coordinating the time on everybody's computer?
It's an issue with sweeping the spectrograph in radio sky spectrograph, so we all start sweeping at the same frequency at the same time.
Okay.
Because we want each bin to be, you know, within 10% of each other everywhere.
Okay. My original question was, you indicated that you thought this might be related to changing the K-index between the earlier observations, and either I missed it on the slide or something. What was the spread of or the change in the K-index?
Well, on the first one, it was running right in here about 0 or 1 at that time of the morning.
Okay.
And down here, of course, you know, there's a large on either side, but it's still, you know, 1 or 2 at that time of the morning. So really, the change, and that's why I said the change in the K-index wasn't that great, but there was a change. So maybe it's got something to do with it, maybe it doesn't, we don't know. Back there.
We're not sure if there are ionospheric blobs moving over this, you know, some one of the stations and not another one, and that's causing some refraction. Then as far as the timing goes, the public computer clocks are probably good within a fraction of a second, but we do want to synchronize the actual sweeps to each other so that all the instruments are sweeping at the same time.
It's a shell within a shell issue then.
Yep.
Yeah, I agree that it would be good if you could synchronize in order to correlate. As you will see in my presentation, I took 2 events that were posted on the radio list a few months ago. I tried to see, because the radio emissions are turning around Saturn, and I tried to see how long it took for the beam to go from one station to the other. And it is of the order of 20 milliseconds. So this is the kind of accuracy that you really need to have if you need to understand it. You want to understand that. Then maybe you should look at this K-index is a good thing. There are probably other geomagnetic indices that you should look at.
Absolutely.
This one is an estimated one. So maybe you should go back to the one that are measured.
the ones that we tried to look at were this right here. This is the US Tech, the total electron count. But there again, this is a model derived from GPS satellites, which may or may not have much to do at HF, and may or may not have much to do at each station, because again, it's a mathematical model, but you don't get perfection. You have to. Exactly, right, it's a good guess. Anybody else? I do want to mention real quick that the article about timing that was supposed to be given here will be on the little thumb drive.
Oh, sure. Could you go back to the previous slide, please?
This one?
Interesting. It looks like you have more than a timing problem.
I think we have an ionosphere problem, which is why K-index came to mind as a possible cause for that, as something that would disturb the ionosphere. There could be a lot more, like everybody said, there's probably more than the K-index, but that's one factor.
One of the other factors is the difference in the gain of the antennas at the different stations. Dave's array of 8 antennas versus, 5-hole pair gives you quite a bit.
So that alone could account.
It certainly accounts for some of it.
It accounts for some of it, but it doesn't account for, you got a big blob here, and you would see that 10 miles away if it was actually there.
Well, actually, if it's ionospheric discrepancy, small scale is what.
That's what I mean. It's not just.
And because it's non-linear optics, so
Right.
you will have amplifications. It's not just simple reflection. So
Right.
that's possible. I wouldn't be surprised that it's just.
Yeah, I would say these spectrograms here are probably, timing-wise, on the horizontal scale, accurate to within probably 5 to 10 pixels of each other, easily. So, stuff lines up pretty well.
Why do you have the lines on the three and at the top one?
Because I'm using circular polarized antennas, and these three are using linear polarized antennas. So what we're seeing in these bottom three are the Faraday band,
Okay.
which doesn't show up with circular.
So you don't correlate at all. You're using totally different antennas.
Right.
But yeah, that's.
I mean, you could still correlate, but it would be difficult to do.
You're measuring different things.
Anybody else? All right. Thank you.